our second talk of the day. We are happy to have Colin McSwiggen from NYU telling us about sampling matrices from HCIZ distributions.
Right. Thanks a lot to the organizers for inviting me to present at this workshop. Everything that I'm going to talk about today is joint work with Nishith Vishnoi and also with Jonathan Leek, who gave the previous talk. I'm going to talk about a couple of new algorithms for sampling matrices from Harish-Chandra-Itzykson-Zuber or HCIZ distributions. These are distributions with exponential densities on orbits of the unitary group as it acts on the space of n by n Hermitian matrices. And these sampling algorithms have applications to differential privacy, quantum information, statistics. I'm going to talk about a couple of these applications at the beginning as a way of motivating the main results that I'll show you later. So the first motivating example is to something called differential privacy. So for some background, imagine the following situation. You are some institution like the Census Bureau or Netflix, and you want to release some data set, disclose it to the public. So if you're the Census Bureau, maybe you want to release census data so that it can be analyzed by economists or sociologists. If you're Netflix, maybe you want to release a bunch of user data so that it can be used in the Netflix challenge so that independent researchers can help you to design a better recommendation system. The problem is that this data concerns some population of individuals, and the data related to individuals is private. It's confidential. So Netflix found this out the hard way. It turns out that people really don't like it when you publish a list of all the TV shows that they've been watching. They were sued over this, and they had to cancel the second Netflix challenge. And the irony is that they had actually tried to anonymize their data, but we know very well by now that ad hoc anonymization schemes are extremely prone to failure. It's just very hard to anonymize data successfully in an ad hoc way. So what you need if you are going to try to release a big data set that's important that remain anonymized is some kind of provable privacy guarantee. So here's some intuition for how a system that provides that might work. Instead of releasing the data directly, you could release a random permutation of the data such that changes to the information of a single individual are hard to detect. That is, you want to use the randomness to guarantee that the probability of any event that depends on the output data can only vary negligibly as a function of data associated to any individual. And as a consequence, it's difficult for someone observing that output to infer what the data associated to an individual was. So that's sort of how the intuition for how such a system might work. Here's a formal definition. A randomized function f is called epsilon differentially private if for all input data sets d1 and d2, which differ only on a single user in a sense to be defined, and for all s in the range of the function, the probability of the event that the function applied to d1 lies in the set s is at most equal to e to the power epsilon times the probability that f of d2 lies in that same set. Now note that because this has to hold for all input data sets, this inequality is reversible. So all that this tells us is that the probability of these two events can't be too different. Now, the formal meaning of this phrase differing on a single user is going to depend on the application. For all of the cases that I'll talk about in this talk, the input data sets D1 and D2 will be matrices. And by differing on a single user, we simply mean that the spectral norm of the difference of those matrices is at most 1. Now, why would you want to use this definition? Well, it turns out to have some really good properties. So for example, differential privacy defined in this way is robust under repeated application. So if I have some epsilon differentially private function and I apply it k times to different data sets that might overlap, and I show you the output of all of those data sets, that combined function is still k times epsilon differentially private. Likewise, it's robust under post-processing. So if I input the output of a differentially private function into another function and tell you the output of that function, that's still epsilon differentially private. All right. So how can we implement a differentially private function in practice? Well, we want to output something that's close to the original data so that it's still useful, but which is random enough to give the privacy guarantee. And this suggests kind of a promising approach, which is that we could try to sample from a distribution that is peaked around the input. And this leads to our first concrete motivating example, which is the problem of differentially private low rank approximation. So in this problem, you are given an n by n complex positive semi-definite matrix, and you want to output a rank k approximation to y, which is the input matrix. So Specifically, what we mean in this case is you want to output a matrix P, which is a rank K projection. So script P sub K is a set of rank K projection matrices, such that the inner product of Y with P is maximized. So these angle brackets here and for the rest of the talk will just indicate the Hilbert-Schmidt or Frobenius inner product of matrices. We just think of each matrix as a point in a Euclidean space where the real and complex part of each entry are orthonormal coordinates, and we take the ordinary inner product. Intuitively, a way that you can think about this is that the subspace that P projects onto kind of captures most of the information about how Y acts. That is, if we project onto that subspace, apply Y, and then project again, we should get an operator that is as close to Y as possible. Now, there's an easy way that we could do this that you might already have thought of. That is, we can just plug Y into an eigensolver, find the eigenvalues or the eigenvectors that are associated to its top K eigenvalues, and project onto their linear span. The problem for this application is that then the output will be deterministic, and we want to solve the problem in a differentially private way. So there are real applications where being able to do differentially private low rank approximation is important. So in the context of the Netflix challenge, this matrix might be, say, a covariance matrix of user preferences. And in that context, the low rank approximation serves as a kind of noise reduction. It can help to filter out spurious correlations. Now, there's a general approach to differential privacy, which is based on the sampling idea from the previous slide. And this is called the exponential mechanism. In this context, what we know is that in order to achieve epsilon differential privacy, it is sufficient to efficiently sample the output matrix from a probability measure with density with respect to the uniform measure on rank K projections that is given by e raised to the power of epsilon times the inner product of Y with P. As you can see, this distribution is exponentially peaked around the matrix that maximizes this linear function. But prior to the results that I'm going to present in this talk, it wasn't known that an efficient sampling algorithm actually existed. As far as we know, the only results were in the rank 1 case due to Kapralov and Talwar. As another motivating example, which also makes a connection to the previous talk by Jonathan, we can consider the problem, the following problem, which is related to quantum information. So this setup will be familiar to those of you who saw the previous talk, but I'll recap. A state of a quantum mechanical system can be represented by what's called a density matrix, which is just a positive semi-definite matrix of trace 1. The set of all n by n density matrices is the convex hull of the set of all rank 1 projections, that is density matrices with rank 1, which in the context of quantum information are often referred to as pure states. So given a density matrix A, we would like to have a canonical way to represent it as a convex combination of pure states. What this means mathematically is that we would like to have some probability measure on the set of all pure states whose expectation is equal to E to A, which is in some sense canonical. And there is a well-established way to do this via the principle of maximum entropy. So we choose the distribution over the pure states that has the largest entropy among all distributions with expectation A. Now, as Jonathan discussed, here we're in a continuous setting. We have to be a little bit careful about what we mean by largest entropy. Here, what we really mean by largest entropy is the smallest Kullback-Leibler divergence from the uniform distribution on the space of pure states. And this minimum value of the Kullback-Leibler divergence is called the barycentric quantum entropy, and it's an important measure of entanglement. So it tells us in some sense how entangled the state A is. Now, the fact that you can actually compute these maximum entropy distributions is something that Jonathan talked about in the previous talk. The maximum entropy distribution satisfies a convex optimization problem, but it's a problem in an infinite dimensional space, a space of all probability measures on this manifold M of probability measures, or sorry, of probability measures on M. So here's that problem. We're trying to minimize the Kullback-Leibler divergence. Here, nu is the density of the measure that we're trying to find. Mu is the uniform measure on M. This first constraint just tells us that the expectation of the density that we're looking for has to be equal to A. The second constraint tells us that this does need to be the density of a probability measure. It needs to be non-negative and integrate to 1. So this is an infinite dimensional problem, but we have strong duality, which lets us reduce to a finite dimensional dual convex program. And it turns out that the maximum entropy distributions have the form e to the power of inner product of y star with x for some optimal y star. So Leake and Vishnoi showed that y star can be efficiently computed, but they also raised the question of whether one can actually sample from the resulting distribution. And the results of this talk will answer that question in the affirmative. So both of these motivating examples are actually special cases of the same problem. To see this, first observe that in each case, the manifold that we're sampling from has some symmetry. It's invariant under conjugation by unitary matrices. That is, if we take a rank 1 or a rank k projection and we conjugate by some unitary, we get another rank 1 or rank k projection. In fact, these manifolds are both exactly equal to the conjugation orbits of specific Hermitian matrices under the action of the unitary group. So more generally, for any n by n Hermitian matrix lambda, we can define its unitary orbit O lambda to be precisely the set of matrices that are generated by conjugating lambda by all unitaries. And this is exactly the set of Hermitian matrices that have the same eigenvalues as lambda. On such an orbit, there is a unique probability measure that is invariant under this conjugation action, which we'll call mu lambda. And this is obtained just by starting with the Haar probability measure on UN and pushing forward by the map that sends U, a unitary matrix, to U lambda U star. So with this setup, both of the examples that we've discussed so far are then special cases of the following problem. Given two n by n Hermitian matrices lambda and y, we would like to efficiently sample from the probability measure with density with respect to mu lambda proportional to e to the y inner product with x. So it turns out that distributions of this type are extremely important in physics and in random matrix theory, where they appear in a superficially different form. And in particular, there is a famous formula that Jonathan also mentioned called the HCIZ formula, which gives an exact expression for the partition function, or really the integral, of the distribution with density e to the trace y u lambda u star with respect to Haar measure on the unitary group. So I'll say more about the HCIZ formula in a bit, but for now, the key observation is that if we send u to the matrix u lambda u star, then this HCIZ distribution on the unitary group pushes forward to exactly the distribution that we want to sample from on the orbit. So there are kind of two sampling problems that are equivalent. We can either solve this original sampling problem on the orbit, or we can just sample matrix U from this density on the unitary group, conjugate lambda by that, and then output U lambda U star. So the general problem that we want to solve then is given y and lambda, can we efficiently sample from either these HCIZ distributions or from exponential distributions on these unitary orbits? And the fact that we can do this is the main result of this talk. So specifically, given some c greater than 0, we provide two different algorithms that sample approximately from the desired distribution on the orbits with error c. Again, as far as we know, the only existing work on this was in the rank 1 real case due to Kapralov and Talwar. What I mean here by the rank 1 real case is that they only consider the orbit of this diagonal matrix with 1 followed by a bunch of zeros, which gives rank 1 projections, but they consider its orbit under the action of the real orthogonal group rather than the complex unitary group. So I said that we'll give two algorithms. The differences between the two algorithms are in 2 points. One is the sense in which we achieve this error c, and the other is the running time. So the first version of the algorithm approximates the measure that we want to sample from in total variation distance, and the number of operations is polynomial in log 1 over the error. The second version of the algorithm approximates nu with error in infinity divergence, but the number of operations is polynomial in 1 over c, 1 over the error, rather than a log 1 over the error. So here are the definitions of those two senses of the error, just for those who aren't familiar. The salient point is that the infinity divergence is an upper bound on the total variation distance. So the second algorithm gives a tighter error bound. However, the trade-off is that the asymptotic runtime is longer. We'll leave it as an open problem to determine whether you can in fact sample with infinity divergence error with runtime polynomial and log 1 over the error. If you could do that, that would subsume both of these theorems, and we could only have a single theorem instead of two.
Is that what does the capital Talwar get that runtime? Capital Talwar gets log 1 over c, but only gets an error bound until variation. Okay. So these algorithms have applications to a number of problems that arise as special cases of sampling from HCIZ distributions, including both of the motivating examples that I discussed, so sampling from max entropy distributions on unitary orbits, and also epsilon differentially private low-rank approximation in complex vector spaces, as well as sampling from complex matrix orange bound distributions that arise in directional statistics. Now, most of the rest of this talk is going to be devoted to describing our sampling algorithms and sketching the proof of the main result. But before that, as promised, I want to say a bit more about the HCIZ formula. So this is an exact formula that gives the integral of the function e to the trace yu lambda u star with respect to the normalized Haar measure on the unitary group. So here, big Y and big lambda are two Hermitian matrices, and the little y's and lambdas on the right-hand side are their respective eigenvalues. So in this formula as written on the slide, we have assumed that the y's and lambdas are all distinct. Obviously, otherwise the denominator vanishes. But it's not too hard to see that in situations where y or lambda have coinciding eigenvalues, the numerator vanishes to the same degree, and you can get another exact formula just by applying L'Hopital's rule to this expression. So we can think of this formula as giving the partition function for the HCIZ distribution on UN, that is just the normalizing constant that makes the HCIZ distribution into a probability measure. But this integral is absolutely ubiquitous in a bunch of other settings in contemporary math and physics. So it was originally shown by Harish-Chandra in the 50s in the context of harmonic analysis on Lie algebras. It was then independently rediscovered by Itzykson-Zuber, two physicists, in the late 70s, early 80s in the context of gauge theory. But it shows up all over the place. So just to sort of list a smattering of examples in random matrix theory, it appears in expressions for the joint spectral densities of Wishart matrices, which model sample covariance matrices, correlated Gaussian matrices, and several other important random matrix models. In quantum field theory, as I already mentioned, it shows up in models of the strong nuclear force. Those are the gauge theories I talked about. But in a simplified setting where space-time is discrete, in representation theory, you can use integrals of this form to write down the irreducible characters of the general linear groups. In symplectic geometry, you can interpret this as a Laplace transform of a Dostermatt-Hecklin measure associated to a torus action on a flag manifold. It also arises in combinatorics and the study of lozenge tilings. It has an interpretation in enumerative geometry as a generating function for the monotone double Hurwitz numbers, which count a certain family of Riemann surfaces. And because of the connection with Wishart matrices, this formula is also used a bunch in high-dimensional statistics and in signal processing. So in statistics, Wishart matrices are used to model noise in sample covariance estimators, particularly for large data sets. And in signal processing, it turns out the complex Wishart matrices control the channel capacity for multiple input, multiple output antenna systems. So this is used for performance analysis for antenna arrays. And there are plenty of other examples. Now, the point of telling you all of this, aside from the fact that I think is interesting, is just to point out that given the ubiquity of the partition function for this distribution and the wide range of situations in which one needs to be able to calculate it, it's kind of surprising that we only now have an algorithm for sampling from the distribution itself. Also, the fact that this at first somewhat funny-looking function turns out to be a very common object is, we hope, an indication that the sampling algorithms as well may continue to find applications that we haven't thought of yet. So
for instance, do you know what the applications are for having full weighted compute these intervals or full weight samples? Like especially in representation, there used to mention that they show you something about records of Like what problems would
why is it user representation theory? Okay, well, in the context of representation theory, this integral shows up in the, I mean, essentially this is the integral that shows up in the Kirillov character formula for the unitary group, or more generally for the general linear group. So there's this whole program in representation theory called the Kirillov orbit method, and this is kind of the central formula in that. I mean, it's kind of a long story, but if you're interested in applications for representation theory, Kirilov's book, Lectures on the Orbit Method, is a really good place to start.
I think I'm curious, as like, would those applications need algorithms? Like, what are the algorithmic questions?
In representation theory, I don't know. Yeah, we have not worked on applications to representation theory specifically, but I would be happy to talk about it afterwards if that interests you. So to sort of start sketching how the algorithm actually works, the algorithm exploits the symmetries of the unitary orbits and of the HCIZ density itself. And to do so, it relies on a kind of inductive or self-reducible structure in the problem, but not quite in the usual sense of self-reducibility. So usually what we mean when we say that some computational problem is self-reducible is that an instance of the problem of a given input size can be efficiently reduced to an instance of the same problem with a smaller input size. So if given a problem instance of size n, if I can reduce in polynomial time to an instance of the same problem with size n minus 1, then obviously I can solve the entire problem in polynomial time. Often the key to making this kind of approach work is an efficient algorithm for computing some relevant partition function. So here is a simple example to illustrate this. So we'll consider the case of uniformly sampling a perfect matching of a graph. So a perfect matching is a list of edges in a graph such that each vertex in the graph has exactly one edge in that list that is incident on it. So another way of thinking of this is you are just pairing off vertices in the graph. Each vertex can only be paired with one other vertex, but you can only pair vertices that are connected by an edge. So if I want to uniformly sample from the set of all possible matchings of a given graph, I can do so as follows. I start off by choosing just any edge E in the graph. I then use my partition function oracle. So in this case, the partition function that I want to be able to compute is just the function that, given any graph, tells me the total number of matchings of that graph that exist. So I use that oracle first to compute the number p of matchings that contain E. So the number p of matchings that contain E is just the number of total matchings of the graph that I would get by removing E and the two vertices that it joins, right? And then I also compute the total number of matchings of the graph that may or may not contain E. So then I flip a biased coin, and I include E in my final matching with probability equal to P over Q. In the next step, I construct a smaller graph, and I do that as follows. If I did not choose to include E in my matching, then I just remove that edge. If I did choose to include E in my matching, then I remove the edge, and I also remove the two vertices joined by E and all of the edges incident on them. And then I just apply the same algorithm to this smaller graph, adding one edge to my list at a time. And when no vertices are left, I know that I've finished, and I just output that list of edges. I know that it will be a uniformly sampled perfect match. So in the problem that we're studying here, we're in a continuous setting, and we do have a formula for the partition function. That's just the HCIZ integral that I showed you on the previous slide, but it's not actually clear how this helps. And the reason that it's not clear how this helps is that it's not obvious how to reduce the problem size. So there are a couple of ways that you could think of to try to reduce the size of the problem, right? Like you could potentially try to sample your matrix, one entry at a time or one row at a time. The issue is that it's not clear that this actually gives you an instance of the same problem, right? Sampling the first m rows of a unitary matrix is a priori quite different from sampling an n by n unitary matrix. Moreover, there are correlations between the rows and between the entries. We need the output to lie in a fixed unitary orbit, and those unitary orbits are cut out by a big list of algebraic constraints, right? Like the entries in the matrices have to satisfy a bunch of polynomials that come from the fact that they have to have the form u lambda u star for some unitary u. If you try to sample row by row or entry by entry, you sort of build up a bunch of dependencies as you go, and the constraints start to change, and it's not really clear that after you sample an entry, you're going to have an instance of the same problem that you started with. So instead of taking an approach like this, what we do is to take advantage of a natural self-reducible structure in the geometry of the unitary orbits. And that's going to be the starting point for the overview of the proof. So to recall our goal here, we're given Hermitian matrices y and lambda, and we want to sample from the distribution with density proportional to e to the inner product of y with x, d mu lambda of x. All right, so first let's look at the simplest case, where y equals 0. In that situation, this distribution just is mu lambda, right? It's just the uniform distribution on the orbit. What that means is that in order to sample x, we can just sample a Haar random unitary, conjugate it, or conjugate lambda by it, and output that. So in this situation, we've reduced the problem to sampling a Haar unitary, which you can do as follows. We know that the eigenvectors of a unitary matrix are uniformly distributed on the unit sphere in Cn, conditional on the fact that they have to be orthonormal. So we start by just sampling any standard Gaussian n-dimensional complex vector. We normalize it so that it lies on the unit sphere. Then we restrict to the subspace that's orthogonal to that vector and repeat until we have a list of n vectors, and those are just the columns of our matrix. That's a Haar unitary. Then we conjugate lambda by that, and that's the matrix that we wanted. Unfortunately, this kind of simple approach does not work for any other value of y. The issue is that this density on the orbit, or the exponential density on the unitary group, stops being unitarily invariant. It's no longer a constant density as soon as you have y non-zero. So we don't have this kind of like conditional independence between the columns of the unitary that we want. We sort of run into the same issue that I talked about on the previous slide, where the columns are correlated. So we need some other approach. So instead of thinking about like columns or entries, the idea is instead to view matrices in terms of their eigenvalues. Now you might object that all matrices in the orbit O lambda have the same eigenvalues, and that's true, but we're not going to think just about the eigenvalues of the full matrix. We're going to think in terms of the eigenvalues of all of the leading submatrices. So that is, we're going to look at all of the k by k matrices that lie in the upper left corner of the matrix that we're trying to sample for k from 1 to n. And it turns out that if you know the eigenvalues of all of the leading submatrices of some Hermitian matrix X, these almost fully determine the matrix X. That is, they determine its eigenvectors as well up to a complex phase of the entry. So you sort of know the absolute values of the coordinates of all of the eigenvectors. Yep.
What do you mean by leading? I didn't understand it.
Oh, by leading, I just mean like they lie in the top left corner.
But shouldn't there be one k by k matrix in the top left corner?
Oh yeah, but for different values, okay. Looks like this, right? Yeah. So we're looking at all the corners. So it's the first one, second one, and the third one. Does that make sense? Cool. So there is a well-studied map that maps a Hermitian matrix to the collection of eigenvalues of all of its k by k principal minors or leading submatrices. This is called the Rayleigh map. And we think of a point in the image of the Rayleigh map as a collection of lists of eigenvalues, which are in each row in descending order, and we'll kind of arrange them in a triangle like this. So here, R11 is just the top left corner entry. R12 and R22 are the eigenvalues of this 2x2 block considered as a matrix by itself. And then the bottom row, this is a 3x3 matrix, is just fixed equal to the eigenvalues lambda that we started with. All right, so to get a better feeling for the Rayleigh map, let's consider the case of rank 1 projections. So in this situation, the matrix lambda that we're starting with is just this matrix E1, the diagonal matrix whose diagonal consists of a 1 followed by zeros. The unitary orbit of this matrix is the space of all rank 1 projection matrices, which geometrically is just a complex projective space. So in this situation, the Rayleigh map is fairly simple. It's actually going to map the orbit to the standard simplex, as Jonathan talked about in his talk. So to see this, note that at most one eigenvalue of each leading submatrix of a rank 1 projection can be non-zero, right? If X is rank 1, then all of its leading submatrices have to be rank at most 1. We also have the Cauchy interlacing theorem, which says that the eigenvalues of the n-1 by n-1 leading submatrix interlace the eigenvalues of the full matrix. And this gives us the sequence of inequalities that relate the largest eigenvalues of each leading submatrix. So we have only n coordinates in this point in the image of the Rayleigh map that can be non-zero. And we have a simple linear transformation that maps these coordinates to the standard simplex. If you consider all of these differences, which if you just think about the traces of the leading submatrices, these are just equal to the entries in the diagonal of the matrix. These all have to add up to 1. So the diagonal of the matrix gives a point in the standard simplex, which encodes the leading eigenvalues of all of these submatrices. So what we see in this case is that the Rayleigh map projects a non-convex manifold onto a convex polytope. But what about the general case of more general unitary orbits? What we'll find is that the Rayleigh map always maps the orbit to a convex polytope, and also that the exponential density transforms nicely under this projection. So to see how this works, again, recall the Cauchy interlacing theorem. The eigenvalues of each of these blocks have to interlace the eigenvalues of the next largest block that contains it. So this is why we write down these coordinates R in a triangle. We have this triangular set of inequalities that relate them, called the interlacing inequalities. If we fix the bottom row of this triangle to be equal to lambda, we have 1/2 n times n-1 remaining entries in the triangle that can take other values. If we think about these as points in 1/2 n times n-1 dimensional vector space, then these inequalities cut out a convex polytope, which is called the Gelfand-Tsetlin polytope of lambda. And what the interlacing theorem says is that the Rayleigh map maps the orbit into this polytope. But it turns out that we can say more than that. The Rayleigh map maps the orbit onto the polytope as well. And moreover, the uniform measure on the orbit under this mapping projects to the uniform measure on the polytope. So if I give you a uniform random Hermitian matrix with fixed eigenvalues, you know nothing about the eigenvalues of the leading submatrices except that they interlace. Essentially, the interlacing theorem tells you everything that you know about the eigenvalues of the leading submatrices of a uniform random Hermitian matrix with fixed eigenvalues. Moreover, this exponential density on the orbit also maps to an exponential density on the Gelfand-Tsetlin polytope because it one can show that it's constant on the fibers of the Rayleigh map. That is, the pre-images of any given point all have the same value of this exponential function.
Why is diagonal here at this point?
Yes, y is diagonal, although it doesn't. Yes, y is diagonal. We can essentially assume without loss of generality the y is diagonal.
But then you should pick the Rayleigh map to be also
To be
like, yeah, I think the blocks to be the same basis as the y basis or not.
Well, in this situation, we're just thinking about the eigenvalues of.
But it's the eigenvalue of particular blocks that makes.
Yes.
So does it like those don't have to be related to the eigenbasis of y?
I'm not sure I understand the question.
I guess maybe like is it true that whatever the eigenbasis of y is, that's the basis in which you have to like choose these minors?
No, we're okay. So we're thinking. Okay, think of these matrices as operators on some vectors on some Euclidean space, or some complex Hermitian space. We pick an orthonormal basis to begin with, and that fixes the matrix entries.
Yep.
So we can really identify each matrix with just a grid of numbers, and we're looking at the rectangle in the corner.
But yeah, this fact about the fibers have constant density, that doesn't matter on what basis y is diagonal at all.
It might.
That's what I thought that you'd say no.
But yeah, I mean, yeah, it's fair. You said it's diagonal, so maybe
I think you're right. We might have to. Yeah, but if we don't take y to be diagonal to begin with, we can always diagonalize y and then kind of undo it later just by conjugating the result that we get by something else. So we can always reduce to the case where y is diagonal, so we do have something that's constant on these fibers. Yeah. Yeah, right. The point is that when you expand out this inner product, you want to get something that only depends on the diagonal entries of y and the diagonal entries of x. And then by taking the differences of the traces, you can write the diagonal entries of x in terms of things that you know just from this polytope, because it only depends on the eigenvalues of the submatrices. But yeah, I think that for that you do want y to be diagonal. But again, it's not a difficult assumption to remove. All right. So because our density behaves nicely under this projection, this suggests an algorithm. That is, we're going to perform two steps. In the first step, we're going to sample a point R from the exponential density that we end up with after we take this push forward to the Gelfand-Tsetlin polytope. We're now sampling from a convex set, so we can use techniques that work in a convex setting. And then we will transfer the sample from the polytope to a sample from the orbit. The fact that this density is constant on the fibers means that after we sample a point in the polytope, in order to transfer that to the orbit, we just need to sample uniformly from the fiber over that point. So the first step uses some pre-existing general algorithms for sampling from log concave densities on a convex polytope. The push forward density to the polytope is still exponential, so it is log linear and therefore log concave. We have very powerful general methods for sampling from log concave densities on convex polytopes. To sample with error in total variation distance, we use a method due to Lavash and Mampala, which runs in time polynomial in log 1 over the error. For the infinity divergence error, we use a different algorithm due to Bastley, Smith, and Takurta, which runs in time polynomial in 1 over the error. Both of these algorithms are use Markov chain methods. The total variation distance algorithm uses a hit and run walk. The infinity divergence algorithm uses a modified grid walk. the reason that you get different error bounds and different running times just relates to the convergence rate of these two Markov chains and the sense in which they converge to their stationary distributions. So for step 2, we have to do some additional work. In this step, we want to convert our sample from the polytope into a sample from the orbit. Now, as noted before, given the sample from the orbit, the desired output is uniformly distributed on the fiber over that point. So we need to describe the fiber, first of all, and then we need a way to construct a uniform sample from it. Now, our approach is going to be to build up a matrix in the fiber, one leading submatrix at a time. So we'll start with the entry in the top left corner, which is just equal to R11. And then we will inductively sample a new row and column at each step. So in each step of the algorithm, we are given the k by k leading submatrix xk. We know its eigenvalues, and we want to sample a new matrix xk plus 1 with eigenvalues given by the k plus 1th row in the triangle that we sampled, which we can write in this form with some entry c on the diagonal, and then this vector v and v star off of the diagonal. So it turns out that at each step, this diagonal entry c is deterministic. It's completely determined by algebraic constraints, since you can write it in terms of the entries in the Rayleigh triangle that we already know. And the vector v is uniformly distributed on a product of spheres in some complex vector space. So to illustrate why we should sample v uniformly from a product of spheres, I'll just show you the simplest case, which is where this matrix xk is diagonal and has distinct eigenvalues. For the situation where xk is not diagonal, it's pretty easy to generalize. You just have to conjugate everything by some appropriate unitary matrix. So first note, this point R in the Gelfand-Cetlin polytope that we already sampled determines the eigenvalues of both xk and xk plus 1. The idea is that we'll write down the characteristic polynomial of xk plus 1 in two different ways. First, just writing it in terms of the eigenvalues, and second, by expanding along this last row and column of the form of xk plus 1 that we've written over here. We'll then set these two expressions equal to each other and solve for the modulus squared of the jth coordinate of v. And what we get when we do that is this expression. So this determines the vector v up to complex phases of the entry. All that remains is to uniformly sample each coordinate vj from the complex circle with radius given by the right-hand side of this expression. Now, first of all, you might object, this is supposed to be the modulus squared of some number. How do I know that this ratio of products is actually non-negative? Well, if you look at it for a little bit, it turns out that the non-negativity of this expression is guaranteed by the interlacing inequalities. In the situation where xk does not have distinct eigenvalues, the denominator of this expression is going to vanish. In that situation, you can still take the same approach of writing the characteristic polynomial two different ways and setting them equal to each other. Just when you solve for the vj's in that situation, you'll end up with a slightly more complicated expression. And in particular, on the left-hand side, rather than having just a single vj, you will have a sum of some number of vj's squared equal to the multiplicity of that eigenvalue. So in that situation, you sample those coordinates of the vector v from a higher dimensional complex sphere rather than just from a circle. So that's why the fiber ends up having the form of a product of spheres. As a final note, this fiber sampling algorithm is approximation preserving. So the error bounds that we got after sampling on the polytope transfer without modification to the sampler to the sample from the fiber into our final output. All right. So to wrap up, the main results in this talk were a couple of efficient sampling algorithms for approximate sampling from HCIZ distributions or from exponential distributions on unitary orbits of Hermitian matrices. I talked about a couple of applications to physics, as well as to maximum entropy distributions and to differential privacy. There are also applications to statistics and possibly beyond. To finish, I want to mention a couple of open problems. So one I already talked about, which is whether we can improve the 1/(c) dependence to a log 1/(c) dependence in the runtime for the algorithm that samples with error in infinity divergence. If we were able to do that, we would only need one theorem. It would subsume both of the results that I presented here. The second open problem is whether similar techniques can be used to sample from orbits of the orthogonal group in general, rather than only orbits from the unitary group. Certain parts of the approach that I showed in this talk do work in that setting. Other parts do not. We still have a push forward to the Gelfand-Cetlin polytope. The eigenvalues of a real symmetric matrix do still interlace. The issue is that in that case, the uniform measure on the orbit no longer pushes forward to the uniform measure on the polytope. And in fact, in general, it pushes forward to something that is not log concave. So these Markov chain methods that we use to sample from the polytope really require log concavity. In the orthogonal setting, that log concavity breaks down, and we need something else. Finally, if there's one take home from this talk, it's just kind of one of the main themes of this whole workshop, which is that continuous symmetries can be useful for designing optimization and sampling algorithms on manifolds, particularly for overcoming issues of non-convexity. Thank you very much. Are there any questions?
Questions from online angle?
Nice talk. I have a few questions. Is this working? Is it working now?
Yes.
So the first question is, what does your algorithm tell about sampling semi-standard Young tableau? If you know the connection. or in integer points in this Gelfand-Cetlin polytope.
Right. So I thought about this a little bit when we were first working on this problem, and I remember thinking that there should be an application and then starting to doubt it. So let me see if I can, okay, so one thing that you could do is okay, so you could try to I guess if you just want to sample a uniform random semi-standard Young tableau, you could probably use something like this, at least in the case of the infinity divergence result. Maybe you could just do some kind of like grid walk on integer points in the polytope. Well, I'm not completely certain about what I'm about to say. I think we concluded that if you want to sample from like an exponential density on semi-standard Young tableau, it's no longer clear that if you just do something like sampling a point from the polytope and then rounding, that you actually still end up sampling from something that's a good approximation of the distribution that you wanted to start with. But I wouldn't be able to tell you more specific technical details than that.
Okay, I see. Thanks. Well, the other questions would depend on your answer, but
yeah, I mean, let's talk about it afterwards, particularly if you have ideas for some applications.
Other questions? Okay, I think if there's no other questions, we can thank Colin again. And I think there's